My name is Dan Jabola, and today we're going to be presenting on dynamic response using NX Nastran. So let's just kind of go over the basic agenda for right now. And again, we're just going to kind of introduce the topic, which is what we're doing here, and we're going to briefly discuss the overview of dynamic analysis, mainly different types of solutions and typical applications you might use. For a demonstration today, we're actually going to show how to set up both a frequency response or sine vibration model setup, as well as a random vibration setup. And then we'll conclude the presentation and then take questions and answers after the event. So first of all, what is a dynamic analysis? It's any case where your load is going to be time varying and you might have inertia forces present due to that time varying load. Just to kind of show down here in the right side, we might have it's kind of a graph of your typical loading as you near a certain resonant frequency for a single degree of freedom system. Many times in statics, you might apply a load and you might end up with just a response of 1. But if your load is time varying and happens to couple with the modes of a structure, you might result in some amplification, as kind of shown here, just kind of by this brief graph. So one of the capabilities added to Femap to allow you to analyze for these situations is the dynamics add-on. It adds several solutions: the transient response, which is a time history response; frequency response, one of our focuses for today, which is again response over a range of frequencies; shock spectrum analysis; random vibration, which is for non-deterministic events, where you're going to look at statistical probabilities of certain stresses or responses happening; as well as DDAM analysis, which is a specialized analysis typically used for naval or marine applications. Now, one thing to note is both these applications, most of the solutions use either two methods for dynamic analysis. There's the direct method, which is where it will take the full model and solve the model directly through the equations of motion. Most of the time when you're running a dynamics model, you're going to result in lots of data, lots of output. So you're going to typically use the modal solution, which reduces the matrix, just kind of throwing up the equation down here from an n by n matrix. Let's say you have 6,000 degrees of freedom. So instead of a 6,000 by 6,000 degree of freedom matrix, you're only having to solve with a 6,000 by the amount of modes matrix. So these are the typical analysis solutions. Here's just another overview of the solution types as presented with or included with the dynamic analysis. Again, the modal solution is actually included with the basic solution, but is kind of the core of all these analysis types. Again, this is where you, have prescribed boundary conditions or constraint locations. There's no force input, and you're calculating the natural frequencies of a structure. Frequency response, again, is typically your input's going to be some sinusoidal excitation across a range of frequencies. And it's a deterministic analysis. Your response with this is going to give you a min and max response over a frequency range. There's also spectrum and shock analysis. This is usually a response to a specific time history, deterministic, and will give you the maximum response. The other focus that we'll be looking at today is random. And random vibration is usually used for non-deterministic events. Examples of this might include earthquakes, rock noise, wind pressure, things like that, where you don't have a time history or an exact sinusoidal excitation, but a whole bunch of these happening at once. So what you get out of this response is responses within a specified range of probabilities. So we'll be discussing a little bit more of that in the next couple minutes here. Finally, there's a transient response. This is a direct time history where instead of basing your results off a frequency range, you're actually looking at it versus the time So what are typical applications or areas that dynamics is used in? Well, it is used very heavily within the aerospace industry, which is partly my own background here. We use especially frequency response for if we're wanting to do a sine vibe correlation. If we know a certain sine environment we're trying to verify our structure against, and also random response, which again is usually used to cover perhaps acoustic ranges and other applications in that area. Another area is marine. One specific application mentioned here is DDAM, which is a specialized analysis typically used for many of the military naval applications. Chemical dynamics is another area of interest. Civil and structural applications. You might want to analyze the structural behavior or response due to an earthquake or other seismic or wind loading events that could occur. Heavy equipment, again, you might be generating large vibrations and you have some electronics boxes that might be vibration sensitive. Or anything really where you're going to have a load that is time varying and you're going to have to worry about inertia and damping for the responses. Again, as mentioned earlier, the focus of this webinar is going to be primarily for frequency response, which is going to be the sine vibe analysis, and random response, which again might be used for article verification against an acoustic load environment, or for, I guess, ensuring that you're protecting against an acoustic load environment and other applications. So our first step here is going to be on frequency response. Again, as mentioned earlier, it's heavily used in the aerospace industry for sine vibration tests. And then what it will provide you is a structural response versus a frequency for a specified range. And we do have an example of some of the output that we'll be going into detail a little bit later. This frequency response is kind of used as the basis for our following analysis, which will be random vibration, which takes this data and might use the transfer functions developed from a frequency response to determine your probabilities of different responses in the environment. So today we're going to be demonstrating this using an actual part that we had worked on, a element wheel or filter wheel that carries optics for the Wide Field Infrared Survey Telescope, or WFIRST program. This is a piece that was used as an engineering test unit, and we're very interested in understanding the loads due to a standard sine vibe and a random environment that would be applied to the structure. So for this demonstration, we're going to give a brief overview of this model, and then we're going to go through one of the first steps, is always running modes and verifying your modal results of the system. Then we'll show you how to set up the loads for a dynamic event. And then also show you some of the key points in setting up the analysis deck for this particular case. Finally, we'll go ahead and post-process the data to kind of show you some results of looking at some of the acceleration loads on some particular optics, in this case, this model here. So again, here is the element wheel or filter. What we have modeled here, just to kind of give a brief overview, is both the test article as well as some of the test fixturing. For this particular case, we were very curious about some of the concerns of maybe how the test fixture might couple with the system. So that was also modeled. Plus, we also wanted to understand some of the forces on here. The system is attached at or base driven at the center point here. So for all these analyses, we've actually constrained at this very center point, which is our drive location, with an RBE2. The structure itself is a composite shell that consists of 8 optical locations. We've modeled 6 of them, 6 filters, and then we have mass elements that represent 2 other optical elements of interest as well. For this analysis, we're going to be looking at primarily just what is the acceleration of this system with result of an X vibration direction as shown by the global coordinate system here. So the first thing you're going to do after you've built the model, of course, with any dynamic analysis is run modes. So here we already have a solution set up, and I'm going to show you some of the basic setups for running a modal analysis and things to kind of think about when you're running for a dynamic analysis, both for frequency response and random. The first thing, obviously, is we'll specify a modal solution. And the next thing we really do is we can just go ahead and specify our modes. Now, one thing to note about this is many times you're going to be looking for modes of interest or modes in a certain range of the system. In this case, we are running from 0 to 2000 hertz for our random run. So we might want to analyze for this full case. It's always important to make sure that you're capturing enough of the modal content for some of these other runs. So trying to understand that and analyzing for the full range can be very important for the system. The only other thing I recommend turning on when you're doing your modal analysis is to turn on the modal effective mass fraction. This will kind of give you an idea of what modes are participating in what directions. We'll kind of show that here very shortly. So typically we go ahead and run. In this case, I already have a run set up here. And so we're going to take a look at a couple of the mode shapes. So let me just set that up, set up the contour here for strain energy for our first mode. Just change colors here so it's a little easier to see what's happening. And also go ahead and I believe we have some transparency here for some other reasons. So in this case, we were interested in looking at kind of trying to understand the behavior of the system here. So this is our first mode. You know, we can look at the strain energy and kind of get an idea of the behavior. As we scroll through the modes, we'll be animating some different directions here. And again, we're going to be exciting this in the X direction. So here we might assume that this might be one of these modes that gets excited in this direction as we apply an X loading. Now we can look through the modes to kind of give us an idea of the shape of what we might be expecting in the structure. But one of the more effective ways of looking at this is to actually look at the modal mass fractions out of the FO6 file. So if we head back here, I've actually already set up or post-processed some of this data. What you'll typically get out of the FO6 file is when you run the modal mass fractions is your effective mass percentages or fractions, and as well as summations. When you run the full system, you'll want to check this to make sure that you're capturing at least 80% of the mass participation. And this becomes important as we start looking at the response. If you do not have the full mass participation of the system, you might be missing critical data and under-predicting your response to the system. But what we show here is we're going to take a look at the first 20 modes of the system here. So I've tabulated this to kind of show some different percentages. One thing we're going to note here is we are exciting in the T1 direction. So we're interested in what modes might act in the T1 and perhaps also the R2 direction as well. One thing we'll note here is that as we're looking through this, we'll see that mode 9 has a very large percentage in T1. We'll also note that perhaps mode 1 and 2 have a little bit of R2 factor. And based off the shape of these modes, if we take a look here, you might see that we might be able to get some excitation if we're moving this back and forth along X as well. So by looking at this will kind of give us an idea of some of the behavior of the system. One of the things we can immediately check is that if we know that we have a lot of energy occurring some of these modes, we will probably see a lot of response at these locations. So for instance, maybe your input drive, or maybe something is driving the structure at 80 hertz, then we would expect to see a lot of response coming out of the direction for this mode 2. So again, always run your modes first to try and get an idea of the behavior system before you start running a full dynamic analysis. So now what we're going to do is, once we've gone through the modes, we're going to take a look in more detail at setting up a dynamic analysis. Now typically for the input, you're going to really need to only set up your loads environment. In this case, we were going to set up a load here, and I've already set this up. And we're going to apply an enforced acceleration at the driving location. So if we highlight this, that is node 1 right here at the driving location of the model. Now it's very similar to setting up a typical static analysis with the exception of your time frequency dependence as a function here. So in this case, if we're editing this function, you can see that we are applying a 9.81 scale factor based off of time frequency dependence. So by looking at this, we're going to open up this function to kind of show what the setup for setting this up, setting up this function is. So if we open up this function, you'll see it's a versus frequency function. And you'll see that I've specified from 0 to 2000 the value of 1. Now this is a value of 1 or 1G, and we're essentially developing a transfer function for 1G across the entire system. If we go back to our load, you'll see that we've scaled it up from 9.81 because we need to keep unit consistent with what our model's built in, which in this case is meters kilograms. So we'll have to apply a 9.81 meters per second squared factor to the model. So what we've done is we will go ahead and apply that load, so you can kind of see here the direction of the load of the system that we're going to be applying. The next thing we're going to do is we're going to go ahead and set up the analysis deck. So again, here I have a setup of a solution. So we'll go through some of the basic options for this setup. The first thing here is obviously we need to specify the analysis type. In this case, we're going to be specifying a frequency and a harmonic response. So we go through the options. We'll move to the bulk data page. One of the important options you're going to want to check for almost all these analyses is this ResVec on. This stands for residual vectors. Many times your modes are only capturing a certain range of responses. But what this will do is it'll also take a look at just the basic loading with a static response and kind of remove a lot of the lower mode content to make sure that you're getting some of the energy content or participation from many of your higher modes, and approximates this using residual vectors. So typically, almost 99% of the time, you're going to be turning this on with this ResVec box checked on. The next area setup we had mentioned earlier was the modal analysis tab here. So again, as we had mentioned earlier, you're wanting to make sure that you're capturing that data. Again, from your previous modal analysis, you're might be interested in ensuring that you're capturing that 80% of the content. You'll verify that by, again, looking at your FO6 file. To kind of answer a question that did come up, to kind of come back to this. Again, if you've captured all the modal, ran your full range, you can verify that by checking the summations across this one for T1, T2, T3, and you'll see similar responses for R1, R2, and R3. And so you want to make sure that you're capturing at least 80% and that you're capturing the modes across your entire range of the model. The other thing you're going to want to do is, as mentioned earlier, there are two solution types, direct and modal. So we'll want to check this box for modal. If we run direct, you can see it's just going to run the straight equations of motion across the entire system. So in this case, we'll definitely want to run modal. The next tab here is dynamic analysis. So this is where we're going to specify both our damping in this case modal damping, and also our solution frequencies. Now for damping, damping is obviously very critical because it determines essentially the amount of response of your system. To define damping, you generate a function, and we would do it via three options here. We have structural damping versus frequency, critical damping versus frequency, and Q damping versus frequency. Now, essentially all of these are going to be defining a very similar thing, and so we do have a discussion of the relationship of these types of damping. Critical damping is essentially the amount of percentage, a certain damping percentage that you will show how much the system will be magnified by. And usually the relationship to this magnification factor, or Q damping, would be this relationship here. So 1 divided by 2 times our critical damping. So you can see if the magnification factor is probably the easiest to understand here as far as the response to the system. So if we were running a single degree of freedom system and our critical damping was, for instance, 2.5%, we would expect that if we were running at the resonant frequency of the system, we'd have a magnification factor of about 20. Structural damping is just another method of defining that, and would be, in this case, 5%, because you can see 2 times your critical equals your structural. Many times damping is determined either by using some general standards. In this case, we're using 2.5% for our particular analysis, or many times through test. So those numbers, the determination of those numbers is going to probably be based off best practices and also testing of whatever systems you guys are working on. So here we've already developed this function, so let me go show you the function. In this case, we specified 2.5% critical damping, so you can see critical damping versus frequency, across our full range of frequencies. So if we head back to this, go ahead and we would specify this as our damping. The other tab that is important is the solution frequencies. Now this determines where you're going to actually get your data points of the system. So for every frequency, or every frequency option you choose, or that's determined by these settings here, we'll create a data point which you'll get all the output for the requested nodes for every single data point of the system. So if we request a lot of frequencies, like if you requested the full frequency range, you are going to get a lot of output. So you're going to want to limit that output. We'll show how to do that shortly. Now to define the different types of cards here, do have a small little slide on this. There are several methods that are defined using the Freq or FREQ cards. There's a Freq 1 through Freq 5. The first method is the frequency list methods. This is typically where you're going to explicitly define frequencies by a range. So you might say, I want to have so many frequencies from 20 to 2,000 hertz, either defined linearly, logarithmically, or a variety of other methods. The other option looks at the modal response of the system, and then we'll place points around each of these modes. Most of the time, or almost all the time for a system, you're going to have your highest responses occur at your natural frequencies of the system. So you're going to want to cluster around those frequencies and generate data around those points. So here's just an example of the frequency spread for a frequency 4 card. Now all these can be used in combination. So here you can see I'm using a combination of the frequency 3 and frequency 4 cards in this particular example. When you start working with this, it's recommended to refer to the Nastran QRG for a more detailed look at these particular cards. So once you've specified these options, really the last couple things is specifying the solution, or the boundary conditions that you're going to be using, and the output. So we'll go here, we've again specified our constraints, and our load in this particular case is an X direction acceleration. And then we're going to specify our output requests. Now typically this is set to full model. In the case of dynamics, you're going to almost never want to use full model. If you use full model, it's going to generate data for every single point or every single node on the system for every single frequency point you choose on the model. If you do that and run full model, it's going to take a long time to run and take up a lot of space. So it's always recommended to create groups. So in this case, we've created some groups for looking at acceleration points. Just have a couple pieces of data here. We also have locations for looking for force. This might be in cases of looking at bolt loads on a structure. Finally, we do have some small sections for stress response as well. So we're going to go through these groups here shortly. Some of these groups are shown right here, so let's go ahead and visualize that. Our acceleration nodes are at key points of interest on the system. In this case, our interest is definitely some of our optical elements. We might be interested in understanding what is the accelerations that are imposed on the system due to different loads during our load environment. One very important thing is you always want to include the input location. In this case, you've included node 1 here, where our constraint location is. And we'll discuss that here very shortly. Just to show some of the other options as well, we've also requested output for some of our bolts, as well as some areas of interest for stresses on one of our optics as well. We'll be using this both for random and frequency response. So at this point, we typically hit analyze. This particular problem took about, I believe it was either 20 or 30 minutes to run. And so here, we're going to take a look at what you get with this data. So here, you're actually going to get a results output set for every single point. You can see somewhere in here is one of our first nodes of the system, as well as some of the spread of the nodes here. So I believe it was around 67, 66. And you can see it's clustered nodes around that based on our frequency cards. So with this, the best way of looking at this data is to use the charts, the charting tool. So what we're going to do here is we're going to go ahead and use the create a vector versus output set. We're going to do it via the output set value. We're going to uncheck use all output sets and filter only for a certain case of frequency ranges, in case this is our output from our frequency response run. Here we're going to take a look at, I need to go activate one of these guys so we get the right vectors. Here we're going to go ahead and take a look at the T1 acceleration. So output set value, I'm going to set this again to case and take a look at T1 acceleration. We're going to select multiple nodes. And we're going to be interested in the response at our input location, as well as our optic right here, or the mass element here. So from this, we'll be able to generate kind of a response plot based off this input. So one thing we're going to do, instead of to help identify things, we're going to go ahead and load a chart template that transforms this to log and gives us a little bit easier view, as well as also populating some of our data here. The first thing you always want to verify, does your input match what the actual system is? In this case, you can see here we have a straight line about 9.81 of our input load. So in this case, we have verified that our loading is correct. We've applied essentially a 1G load across the entire frequency spectrum. So here, we can now take a look at some of the responses here. One thing to note is some of the areas that we show high response happen at 64 hertz and about 288 or 287 hertz. If you recall correctly, or if you recall, these happen to be a couple of our response frequencies where we had some R2 as well as our 288 showing the highest response in the system. Again, we're showing running the modal mass participation percentages becomes very critical or becomes very informative in understanding some of the data. What we can do with this data is, here I'm just going to go ahead and remove it so we're only looking at this guy. We can actually, for instance, copy this to a report if you're generating a report, or sometimes you may be post-processing this data as well, and you might copy these chart values and copy them into Excel as well. So from this point, we've actually shown kind of the basics of running a frequency response and also verifying the input data. Obviously, we could do the same thing by looking at bolt loads and any other areas of interest on the model as well. So now what we're going to do is we're going to actually continue working with this and discuss how to take this to the next step of running a random vibration. So first of all, again, what is random response? Random response is used to look at environments that are non-deterministic. So again, this might be rocket noise. You're not going to have a perfect sinusoidal response at 56 hertz with 10 Gs at 56 hertz, for instance. It's going to be very random. So you're going to end up developing a statistical environment and a power spectral density function as your input load for this environment to give you a probability of how likely certain stresses or max stresses will occur in the system. Again, as mentioned earlier, frequency response is the basis for random vibe. So when you run a random run, unless if you restart, it's actually rerunning modes, it's rerunning frequency response, and then performing this function where it takes the input PSD, which we'll discuss here shortly, times your sine vibe transfer function, which is again similar to what we were looking at here in our graph with the response to a 1G load squared, and then it gives you your power spectral density function, or a response spectral density function. So what we're going to do here is we're going to actually go ahead and just kind of show some of the additional steps to setting up a random run that that are needed in addition to the frequency response run. And then what we'll do is we'll again also post-process some of the data to show you some of the output from this particular model. So in this case, we would actually set it up very similar or almost exactly the same for frequency response. We're going to use the same load information here. The other thing we're going to do is we are actually going to specify the input power spectral density function. So what is this input here? Again, this is kind of the input environment that's usually determined by looking at large amounts of time history. Vibration might have some accelerometers, for instance, near one of your input points on a rocket, and from this you'll develop your power spectral density function. Other cases here, you might have conservative specifications. In this case, I'm using a Goddard Space Flight Center spec, the GEVS qualification level in this case, where it develops this kind of ramp to try and ensure that you're covering your system against acoustic loads and other cases. And this is an extremely conservative spec. So you're going to see very high loads on our system, but there's one spec that you might use as an input. It will be our particular input for the system. So if we go back to the model, the first thing you would do, in addition to your frequency response run, is set up your power spectral density function. Now in this case, this PSD, again from our Goddard spec, is in G squared per hertz. Again, these are G units, and this actually will kind of go into why I use the scalar factor on our load definition. These are in G units, and you can kind of see if we go to the log scale, it forms that same shape that we would expect for the system. If we go back to here, we're going to have to scale those G units up into our proper unit system. In this case, they're 9.81, and this will convert them into meters per second squared. So once we've set up the PSD, most of the solution setup is very similar to frequency response. Again, you're going to set up your frequency range and also specify modal. Here, you'll specify your damping and then your solution frequencies using the freak 3 and 4 cards in this case. Here is where we start having to choose some of the new options. We can choose for Nastran to output only the PSD functions. We'll explain some of this output shortly. Autocorrelation functions, or just the raw RMS value. In this case, we're going to request all for both elements and nodes. This output request here is a method of being able to get output from your model without actually having to look at the OP2 file. What this will do is allows you to specify groups to take a look at displacements or forces on a system. And we'll generate these as functions that are input directly in. Now typically when I run, which may not be the case for everyone who runs a dynamic analysis, I'll typically run with summary data only and get most of my data out of the OP2 file. The next tab here, we would actually specify our PSD function. We're going to specify against that frequency response. So in this case, our PSD function can specify the interpolation method. In this case, log is default and used for most cases. So really, when you come to this screen, I usually will specify PSD. Finally, again, same boundary conditions and same reasons for our output. At this point, we're actually ready to go ahead and run a random analysis. So when I'd hit Analyze here, again, it would take some time to run. It's actually running modes, and then the frequency response, and then finally the random output of the system. With this, you're going to get quite a bit of output here. You're going to get the power spectral density function. You're going to get the RMS values, which are your root mean square values. That is probably going to be your core data you're looking for, your positive crossings, and also your cumulative RMS values as well. So let's just go through and explain what some of this output is for. Your primary output is going to be the power spectral density function data, and this is your PSDF output. Typically, this is used for determining high areas of energy content to understand, okay, maybe this mode here is affecting our system. Again, you might get some of this from the frequency response runs, but this will also give you another option for looking at that. Your cumulative RMS data is just another method of looking at where most of your energy is going into, so you might see that a certain mode is moving the data up a lot higher, and we'll show that shortly. The RMS response is one of the main things that you're going to probably be looking at. Your root mean square value is actually the area under the power spectral density function curve, or the square root of that. And this is typically the value you use to calculate against allowables in other cases. Many times you're going to multiply this value by 3 or 3 sigma, because again, this is a probability, and you want to assure that 99.7% of the time that your stress is under this maximum value, so that you only have a case of possibly 0.3% where the stress value might be exceeded. And this is a typical standard in aerospace. Finally, we have positive crossings, which are typically used as, or typically determined cycles per time for different frequency loads. And this is typically used for fatigue analysis. So let's go ahead and we're just going to show briefly what some of this data looks like. So we're going to go ahead and clear this chart, clear our data here. And we'll go ahead and let's do another vector versus output value. In this case, we're going to take a look at random and look at the power spectral density function. Again, here we might look at T1 acceleration, and we're going to look, first of all, at the location of interest. We're going to select multiple, and we're going to grab first our input location and that same optic. So with this, we'll go ahead and populate the data. And we're going to load a different chart just because in this case it's really technically this. So what we want to indicate here, the first thing, again, always check your input. You can see here we have our input curve, our input PSDF that matches exactly what we input into the system, showing that, okay, we are properly loading the system. I'm going to go ahead and remove that and now show this. Here, again, we have the power spectral density function. This is in meters per second squared, the whole thing squared per hertz. And this gives you an idea of, again, where a lot of your energy is going into the system. So we can see, again, at our modes, around 64 hertz, we're seeing a lot of energy in the system, and also 280 hertz, being some of our primary modes of the system. So, perhaps if you're getting a lot of energy there, you might try and either move the response of the system away from that location or try and reduce that response. Other cases, you might say, hey, we want to make sure to isolate these frequencies to ensure that we're not exciting the structure, those particular frequencies. So as mentioned earlier, the area under this is actually the RMS value. So that it can actually be looked at as a raw value of the system. So if we look at RMS values, we'll go ahead and let's take a look at the raw acceleration value of this optic here. So we go to results and take a look at RMS. I'm just filtering for a case here, so it's really easy to get to RMS values. We could go ahead and look at T1 acceleration, also T2 and T3 acceleration, and take a look at the node here. So what we get here is the RMS value acceleration of the system. So this optic is seeing 309.8 meters per second squared RMS value during the excitation in this case. Obviously, we're going to have to multiply this by 3 to ensure that we don't exceed that value by 99.7% of the time. So typically we take this value multiplied by 3, and it ends up being a very high load, about 94 Gs. So you want to make sure that, for instance, this particular optic might not see more than 94 Gs. Again, there might be a lot of things. In this case, this environment is is a very conservative environment, so between force limiting and also possibly determining your actual environment, probably reduce this number by a large amount. But again, this is kind of a conservative check on the model. Finally, we'll just take a quick look at the also another plot of the RMS data. One thing to note is that we can actually look at the stress output on a certain optic. So as we mentioned earlier, we picked out some stress locations on this particular optic. And we might be interested in, for instance, our solid bond Mises stresses on the glass to kind of get an idea of, okay, maybe what are some of the critical values. Again, you'd multiply these values by 3. In this case, this is in pascals due to the rather high numbers here. So by looking at your RMS data and also your spectral density function, you're able to start determining your loads for your environments. And so from this data, you'd obviously be able to use this for helping determine if your structure is going to be able to survive your load environment, or can also use it for correlation to ensure that, hey, we're getting the proper data for the system. So at this point, can go ahead and move on to kind of the conclusion of this webinar. Here I'm going to leave you with a couple tips and tricks. Again, as mentioned earlier, we always want to run modes in the system. So always run modes first. Always make sure that you understand what's going on with the natural frequencies before you start tackling frequency response. So give you a much better idea of maybe ways of fixing, and then when you start seeing high responses, why that might be occurring. Again, you're going to want to check to make sure that we're capturing the full modal content of the system. So again, at least 80% for the different directions, T1, T2, T3, which I did see a question come up referring to that. That's the translations and rotations of the full system. And that you're, again, ensuring that you're capturing your frequency range of interest. Again, another good tip is to always verify the input at your response location. Again, this will make sure that what you're actually putting into the model is correct. And that many times you might forget to scale up your G load, and instead you're only applying 1 meter per second squared of a load as opposed to 1 G, or 9.81 meters per second squared. Finally, turn on residual vectors. And this will just make sure to capture your modal content of the system. So in conclusion, we've shown here some of the capabilities of Femap and how to actually go about setting up a frequency response and random response of the model, and just some tips and tricks on how to actually use this data. Again, some of the other add-ons that we didn't discuss today were the transient response, shock, and also the DDAM analysis. Bulk of the analysis that at least I've run in my experience in the aerospace industry is focused primarily on random and frequency response. Again, also using the modal method for the solution. And again, dynamic analyses are used for a variety of applications and are usually very important, especially if you have a time-varying load and inertia and damping forces might exist in the system. So again, it's a very powerful tool for being able to verify that your structures are going to be able to meet your loads environments and be able to survive whatever loadings you might be applying to them. So at this point, I'm going to hand it over to Aswin. If you want to take over, Aswin, to be able to kind of give a little bit of a company overview, and then we'll end with a question and answer.
Thank you, Andrew. So thanks so much for covering all that. That was a lot of information that was covered. So if you have any questions, please type it into the questions panel on the GoToWebinar, and Andrew will be looking over that right now. I just want to give a quick overview of SDA. We're a team of 14 engineers. We design lightweight and load-efficient structures, specializing, working with companies that require high-level analysis, specifically in the aerospace industry, and working with companies like NASA, Lockheed Martin, Piper Aircraft, and Aurora. And we specialize in composites and lightweight structures. So to do the analysis, we use tools such as HyperSizer, Femap and NX Nastran, Fibersim, NX, and Simcenter 3D, Dyna, and much more. And we resell and support some of that software, including Femap with NX Nastran, Simcenter 3D, also known as NX CAE, and Fibersim, Solid Edge, and HyperSizer. So in June, if you're interested in learning more about Femap with NX Nastran, we have a class from June 13th to June 15th at our office in Sterling, Virginia. And the cost for that class is $1575, and you can learn more about that at Structures.Aero/Femap-training, and just we'll be sending out these slides, so you can just click the link there. And we'll be covering, it covers all aspects, getting you ready to use Femap at your workplace, so that goes from geometry preparation all the way to post-processing tools. If you're interested in the dynamic response add-on that was discussed today, it is available for only, it can be acquired for under $3,000. So if you'd like us to send pricing to that, just let me know, and I'm just going to pop up a quick poll just so anyone that's interested in that can, we will contact you about that. Otherwise, you can contact Marty Civic at mcivic@structures.aero. And I'll just let that go for just a second. All right, thank you. So in conclusion, Andrew will be covering a few questions in just a second, and if you have any further questions, his contact information is on the screen, and if you have questions about Femap, NX Nastran, dynamic response, or any of the other add-ons or capabilities, you can contact Marty Civic, our Director of Sales, at mcivic@structures.aero. So Andrew, you want to go ahead and answer the questions?
All right, I'll go ahead and do that. I'm going to hand the control back to me here shortly. All right, so one of the questions came up was, can you show more detail on 80% mass participation rate? Again, I had shown only the first 20 modes, and I was looking through my analysis deck and noticed that even for the amount of nodes up to a frequency of 2,000 hertz, we're only capturing about 65%. So in this case, perhaps I may actually go back and run this even to a higher level. You can see here we're at 694 hertz, and so some of the other frequencies might be higher than that. So that was one case here. You can see here that it does add up quick, but still, even though you might have to capture a lot of modes from the system, and obviously this will be very deterministic on any of the systems here. Another question that I saw came in from, in this case, at Siemens, is, are grid point forces for random analysis available? And if so, are they any use for Femap free body display? The problem with with the data shown here is that this is a RMS value. So you're actually seeing what could be the potentially max value of the system, but it may not occur at the same time another max value occurs. The only way to really get a true free body in that respect might be to run a full transient system, or you're just really not going to be able to get that. Because what's happening is certain things might be acting in phase with each other. So where the maximum of one node, for instance, let's say this guy's getting excited this way, may not be the same time the maximum of this guy is occurring at the same time. So, no, unfortunately, the free body display would not be useful in this case. There have been cases where I actually developed some MPC equations that did some summation forces here to actually look at C bushes. This is done actually on this particular model to capture interface forces. But again, it required a lot of MPC equations to be able to capture that data in phase with the system. Another question that came up from Thomas Coates is involving contact. Now, one thing to note is that you can run a preload, a modal solution with a preload to be able to kind of define contact, to get small deformation contact with, solution 101, and then that would be used as your basis for determining your load path for the system. Now, unfortunately, contact is a nonlinear situation. So if you're worried about, a part separating as it's moving, you're going to have to run a transient or time history solution to really capture that data. You could do that with one of the nonlinear solutions and run a time transient data and essentially be able to get some of that information using some of the post-processing methods. But again, this is going to be very computationally expensive for the system. Another question from Mark Anderson was about use of an RBE2. Now the RBE2 is just uses a rigid point to be able to spread to the constraint locations to drive to a center point. I actually do have RBE3s here in this frequency analysis, mainly for these mass elements. Again, that's mainly the differences between an RBE2 being a fully rigid element and an RBE3 being an interpolation element. And if you have more questions on that, definitely contact us for this. So I'm running through questions here. Question from Sam Range, is it possible to determine which modes are contributing to a specific frequency response solution? This is kind of where you're going to be looking at some of this charting data here. I guess in this case it's an acceleration spectral density, but still is kind of useful. You'd have to correlate this back to your modal participation or your natural frequencies of the system. So here we could see again high energy 64 hertz, high energy 289 hertz. So this is where I'd go back to my particular response here. Again, I'm only showing the first 20 modes and go, hey, look, I see a lot of mode 9 is showing a lot of participation, and also mode 1 is showing a lot of participation. So from here, I would typically go back, animate the response just to understand where some of this energy is going into or how this energy might be going into the system. So here we can see, oh, hey, look, we have the shaft of the system kind of bouncing around back and forth in the X direction. So maybe if we want to reduce that mode's participation, we might stiffen up the structure to try and prevent this mode from occurring. Question from Mark Anderson. I only showed one direction. Typically, yes, you would run all three directions. That's actually why I do have an acceleration X, acceleration Y, and an acceleration Z direction as well. Again, just to verify your system. And this is typically done, in correlation to a test. So you're typically going to match your test setup and run this, and then correlate your values to make sure, hey, my structure is behaving as I'm expected to. Well, I believe at this point in time, I know there's quite a few questions here, and we'll do our best to answer some of these offline in the near future here. I want to thank you all again for attending this webinar, and I look forward to hearing more from you guys if you have questions concerning dynamic response. So I'll hand it back to Aswin to go ahead and conclude.
Great, thank you so much, Andrew. So yeah, if you have any further questions, you can email Andrew at Structures.Aero as listed on the screen. And yeah, thank you guys. And we'll be sending out the recording and slides later tonight or early tomorrow. Thank you.